Just got to get the camera to be on the whole board. There we go. That looks good. Hey, everybody. I think we're recording. And nope, the timer's not going. There it is. Timer's going. Hey, problem 50. You remember it. You remember it. Problem 50. You got this in your notes. That's the curve. There's the point. We're behind all sorts of stuff regarding this curve at this point. And the first thing we got to do is find the Frenet frame, the T, the N, and the B. And I found the mistake. It was about a third of the way through. I think I blew some factoring in here. So remember R prime, easy to do. And R prime of 1, 1, 2, 2, we got that. Yay. Now when you turn this into a unit vector, all you do is divide by its length, and the square root of 9 is 3. We had this, and that's the correct T. Let's see. So it's a 1/3. So throw a 1/3 in front of this, and you've got the T. I've got it written over here on the side. You can't quite see it, but I can show it to you over here. So there's the big T, the unit tangent vector. All right, back to work here. Can we get this going? Yeah, that's good. You cut off the top, but you know what it says. All right, so why do we have big T over here? Because it's big T of T. You're going to have to take its derivative. So you got to leave the little t in there. Its derivative is going to be a chance to use one of our rules. You could do the quotient rule for a scalar being 1 over the scalar. So you have a division problem. A scalar times a vector is okay. It's still a vector. So I can do the quotient rule on this times that plus this untouched times the derivative of that, which we tried to do in class. I think we tried to do it term by term, and I think that's where I went wrong. But you can see the quotient rule comes out forcing this thing to be the common denominator, this 1 over 1 plus 2t squared quantity squared. That's going to be the common denominator, because remember, we're going to be doing a quotient rule on this thing. It's not going to cancel with anything over here. So getting a common denominator, though, for all the terms, you end up with a halfway decent little vector there. Now that's T prime. I think that's the last derivative we had to take, and that's where the mistake was. So front and center on your notes there, just recopy that down. There's a dividing line here because I did T prime of 1, and I did T prime of 1 divided by T prime, the length of T prime, because there's a 9 here. Wait, no, because that 9's there because of the quotient rule. All right, I'm okay. This makes sense. All right. Because you put in a 1, you get a 1/3 squared as a 1/9. So that's my T1 prime, this guy here. And that means we could get N. N is T prime divided by the size of T prime. So here's T prime copied down. That's this thing from over here. Copied it over here again, and then divided by its length. And here's when you know you're living right. 16 plus 4 is 20, plus 16 more is 36. So I got a square inside of the square root. I'm probably doing this problem correctly. We didn't get that. We got uglier numbers if you look. We had some 8s, I think, floating around. It was not good. Anyway, so letting this 1/9 cancel with that 1/9, because square root of 1 over 81 is a 9th. And a 3 pops out because you're taking a square root of 36, which is 6, but then I canceled a 2 out of these guys. So you see that, a 4, a 2, and a 4. So I simplified that, and that gives me big N of 1. So I'm not going to write it in, but to get big B, which is up here, let's see if I can get that up there. Big B, there we go. Big B over here. Big B, you get that from the cross product of T and N. And what's really beautiful is, if you can see these guys, let's get that a little bit higher for you. There we go. Yeah, here we go. So there's big T, big N, and big B. I'm going to get out of the way so you can look at those. Every pair of them dots to 0, so that's excellent. So 50 has, we've got the T, the N, and the B, and the question was, can we get an osculating plane? Can we get a normal plane? Well, let's have at that normal plane. It's easy to do the normal plane because you can remember what it's supposed to be for normal plane. You got to do the two vectors that have normal in their name. So all that work gone because all we need is the t, the n, and the b to do everything else. So let's do the normal plane. And this is a practice, test practice. It's good test practice because we've got two vectors, t. Oh, sorry, we don't use t. We use n and b because n and b have the word normal in their names. So we're going to use n, which is the 1/3 vector, -2, -1, 2. And we're going to cross that with b, which is the 1/3, 2, -2, 1. So here we go. I'm going to just write them in the cross product formation. N cross B equals, we got an I, J, K. I've got a 1/3 here and a 1/3 here. One of the properties of cross product is if you got a scalar in front of all the components of a vector, it's as if it's in front of the entire cross product. So I'm really just going to have a 1/9 times this cross product. So I'm not going to drag all these fractions around. I already know what's going to happen. I've got the -2, the -1, the 2, the 2, -2, the 1, and I'm going to end up with 1/9 vector. All right, so -1 minus -4. That's -1 plus 4. -1 plus 4 is 3. Oh, I like that 3 playing with that 9th. Very nice. Next up, the J. Remember, the J gets the extra minus sign. So I've got -2 minus 4 is -6. Take the opposite sign at 6. That gets to play with this 9. Very cool. Now the K. 4 minus -2 is 6. So that's my normal. The normal to the plane. In fact, I don't even have to use this 9th. I can cancel 3 out of everybody. We're going to use for our normal, since all I want is the coefficients, I'm going to use for my normal a 1, 2, 2. So that's my normal for my plane. It's interesting that if you look at the big T, the big N, and the big B, they're all made of 1s and 2s as well. Can't help but wonder if the author has designed this problem so that everything works out nice, but you don't get much variation. So now I've got a normal to the plane. This thing is perpendicular to the plane that we seek. So that means that I have x plus 2y plus 2z equals big D, and that's where that point, which we haven't looked at in so long, but we have the point 0. Oh, was it a 2, 1 or a 2, 2? 0. Oh, it's on the other page. Hang on, I'm with you. I'm with you. Stand by. 0, 2, 1. 0, 2, 1 goes right in here. 0, 2, 1. My D is 6. What a surprise. Yeah, we had 6 floating around in this problem quite a bit too. So the normal plane is going to be this thing equals 6. You have to be able to do this kind of stuff. So it's nice that you have a test next class, and the following chapter uses those skills to kind of reinforce them. So even though we're working on chapter 13, we're using skills from chapter 12. Now, let's do a pure chapter 13 problem. This was not requested. I know the book asked for the osculating plane. It's the same thing. You take the two vectors for the osculating plane, cross them, get the normal to the plane, use the point 0, 2, 1 to find the D. You get the equation. You should be good at that, but go ahead and try it. And if you get lost, ask me about it by email, or we can do it before class. Do it before we have the test. Next up, I'm going to do one pure chapter 13 problem based on what we've already done. So it's the same problem, number 50, the same given, but this time let's do arc length. And the reason we know arc length is going to work is because the t, the n, and the b, their denominators were very closely related to what you'd be doing for arc length. So since the denominators would work out pretty good, that means the arc length formula should work out pretty good. So let's take a look at it. It's going to look like this. So this is for the same r that we had before. That's that natural log. And it was the 2t and the t squared. I think that was r. So s of t is going to be equal to, I'm doing the general arc length formula just because I can. But the reason I'm choosing to do is because we have to start with 1. We did an arc length problem in class, maybe 2 of them, and both times they started with 0. If you look at book problems, quite often the S of t formula starts with 0 because they can. But in our problem, we have a natural log t. You can't take natural log of 0. So a good place to start is, how about natural log of 1? Natural log of 1 is 0, so I get an x-coordinate of 0. But the t running in the background is t equals 1. So what it means is I'm going to come up with a function that gives me the arc length always starting at 1. So whatever the curve does, I'm always starting at the point 1. So the curve might do some fancy thing. But I'm going to find the arc length measured from t equals 1, not t equals 0. I hope that makes sense. You're allowed to choose whatever you want for this. But once you choose it, your arc length formula treats this t value as the anchor point. It's where you start measuring your distances from. So let's see what we got here. Square root of, oh, this is a t. I'm going to do this thing strictly by the book. I'm going to be writing the derivatives of these in terms of a dummy letter. I chose the letter u. So I took the derivative of natural log t, that's 1 over t. It is really bad to have the letter t in here with the dt and the letter t up here. It can be very confusing. So I've replaced this 1 over t, the derivative of natural log, I've replaced that with 1 over u, and then I'll throw a du on the end. And those letters are going to go away anyway, because when I substitute in, it's going to be a function of t at the end. Plus, derivative of that is 2, squared is 4, plus derivative of that is 2t, so it's a 2u squared du. And those of you that remember Wednesday's class are going to look at this and say, oh, yeah, we did this. You factor out a 1 over u squared. The square root of 1 over u squared is 1 over u, leaving inside the square root a 1 plus a 4u squared plus a 4u to the 4th. Because, remember, I factored out a u squared, which means when I multiply back through by 1 over u squared, I have to get this back. 1 over u squared times 1 gives me 1 over u squared. 1 over u squared times 4 over u squared gives me 4. 1 over u squared times 4 over u to the 4th gives me 4u squared. So the equal sign's not a lie. And what we saw last class kicks in again. This happens to be a perfect binomial square. So I have the integral from 1 to t of 1 plus 2u squared du. And don't forget there's a 1 over u right there. How do I do this integral? This is a Calc 2 integral. I can go term by term if I multiply through, because I get 1 over u. I know how to integrate 1 over u. And then 2u squared divided by u is just 2u. I know how to integrate 2u. So my integral ends up being the antiderivative of 1 over u, which is the natural log of absolute value of u, plus antiderivative of 2u is u squared. And these two guys are evaluated from 1 to t. So my arc length formula is going to be natural log of t minus natural log of 1, which is 0. So that's gone. I'm going to write that down. Plus t squared minus 1. So my S of t for this curve is a nice closed form. Natural log of t plus t squared minus 1. So whatever this curve does, it grows fastest in the z-coordinate. It starts at t equals 1. So the x-coordinates stay positive. They just grow really slow. The y-coordinates, because we have t equals 1, they stay positive. Z-coordinates stay positive. So it's some curve in the first octant that comes up real fast in the z direction. It's growing kind of faster in the y direction than the x direction. So it curves away from the x-axis and up like that. And starting measuring from t equals 1, which is that point that we had, the 0, 2, 1. Starting from that point, we can measure arc length by just substituting in whatever t happens. So if t is e, the length of the curve from t equals 1 to t equals e would be natural log of e, which is 1, plus e squared minus 1. So that's how you would use this if you needed to find repeated arc lengths. You could do that. Now, could we use this? Could we use this animal right there to do parameterized by arc length? And the answer is not easily, because you can't solve this for t. To do parameterized by arc length, you'd have to solve for t. This is not going to be solvable for t. If you were in a pinch and had to do it, you'd replace the natural log of t by a Taylor series, trying to keep it in terms of t squared. Just the first few terms of Taylor series. You only have an approximate, but you could solve the quadratic for t, and then you could write t as a function of s. And then you'd be able to substitute that in, and you'd have the curve parameterized by arc length. But it's nasty, nasty. So that's the end of my video. I'm going to shut it down. Thanks for watching, you guys. How do I shut this down? I'm going to hit end stream. There we go. Bye. It's still going. End stream. End.